In this video, we're going to take a look at some mathematical laws of probability and see how we can perform algebraic manipulations involving probabilities. These laws of probability can be understood visually with the help of the concept of sets and Venn diagrams. We usually use S to denote the sample space, which is the set of all possible outcomes of the situation concerned. Using the concept of set, we can consider the probability of an event as the area of the set in the Venn diagram. Therefore, we can consider that the area of the sample space is 1, while the probability of the event E is the area of this set. And of course, this area is between 0 and 1 because E is the subset of S. With the Venn diagram, we can easily understand the following laws of probability. Firstly, let's take a look at this one. Here, E prime denotes the complementary event of E, which means not E. We can see that PE prime is equal to 1 minus PE, because PE prime means this area, and this area is equal to PS, which is 1 minus PE. In mathematics, this formula is called the complement law of probability. Next, let's take a look at this one. Here, A union B denotes the union of events A and B, which means A or B. And A intersection B denotes the intersection of events A and B, which means A and B. We can see that PA union B is equal to PA plus PB minus PA intersection B, because PA union B refers to this area, and PA intersection B refers to this area. So these areas have the following relation. In mathematics, this formula is called the addition law of probability. Next, let's take a look at this important formula involving the conditional probability. Here, PB given that A means the probability that event B occurs if event A has already occurred. In other words, to find PB given that A, we mean to find PB. But this time the sample space concerned is not S, but A. So this set A is known as the reduced sample space in this situation. Therefore, we need to see how much B is in A. So by computing the ratio of these two areas, we can find the conditional probability of B given that A has occurred. By making PA intersection B the subject of this formula, we can obtain that PA intersection B is equal to PA times PB given that A. And this formula is called the multiplication law of probability. In other words, PA and B is equal to PA times PB given that A has occurred. By the same argument, we can also conclude that PA and B is equal to PB times PA given that B has occurred. So there are two ways to expand PA and B. On the other hand, for conditional probabilities, since they are also probabilities, so they should follow all the laws of probability. For example, the complement law that we have just learned is also applicable to conditional probabilities, like this. That means given that B has occurred, the probability that A occurs and the probability that A does not occur should also add up to 1. Let's have a quick summary. So far, we have learned these three laws of probability, and the formula of conditional probability is equivalent to the multiplication law of probability. All these formulas are always true for any events A and B. Now let's consider two special situations of events A and B. One is that A and B are mutually exclusive, and the other one is that A and B are independent. When A and B are mutually exclusive, it means that A and B have no outcomes in common. So the Venn diagram is like this, and thus A intersection B is the empty set. Therefore, we know that PA and B is equal to 0. So the addition law becomes simply PA or B equals PA plus PB. And we can also see that the probability of A given that B occurs is 0. This makes sense because mutual exclusion means that if we have one, then we cannot have the other. Therefore, when B has occurred, A can never occur. So PA given that B and PA intersection B are both equal to 0. On the other hand, when A and B are independent, that means the occurrence of A does not affect the occurrence of B, and vice versa. Therefore, in this case, the conditional probability will be equal to the unconditional probability. So we know that PA given that B is equal to PA. In this way, the multiplication law becomes PA and B equals PA times PB. And the addition law can be rewritten as this formula. In other words, PA or B is equal to PA plus PB only when A and B are mutually exclusive. And PA and B is equal to PA times PB only when A and B are independent. After learning these laws of probability, let's take a look at this example. Suppose A and B are two events, PA is 0.32 and PB prime given that A is equal to 0.7. In part A, we need to know whether A and B are mutually exclusive. To test whether A and B are mutually exclusive, we should check whether PA intersection B is equal to 0. From the multiplication law of probability, we know that it is equal to PA times PB given that A. Now PA is known according to the question, and PB given that A is not known, but PB prime given that A is known. So we should consider the complement law of probability to rewrite PB given that A as 1 minus PB prime given that A. As a result, we know that PA intersection B is equal to 0.096, which is not equal to 0. So we can conclude that A and B are not mutually exclusive. In part B, if PB is 0.3, we need to know whether A and B are independent. To test whether A and B are independent, we should check whether the conditional probability is equal to the unconditional probability. In this example, we can try to calculate PB given that A. And then we can find that it is equal to 0.3, which is exactly equal to PB. So we can conclude that A and B are independent. The other way to test whether A and B are independent is to test whether PA and B is equal to PA times PB. We can get that PA times PB is equal to 0.096, which is exactly equal to PA intersection B. So we can conclude that A and B are independent. This is how we can apply the laws of probability to perform some algebraic manipulations.